All right, so we sort of talked about, we did a rehash of the previous, things that we needed to discuss, things about why are we talking about something like Pliron and how it's very similar to or the same thing as MLIR and what is being implemented in Rust, right? And before we broke, we talked about uh, core data structures, right? He said there's context, there's operation, there's pipe, there's attribute, there's parse. At least now you must have a mental picture of what each one of them can be, correct? Context is some data structure that sort of looks like this, right? And then if you wanted to say operation, where's that? Okay. Operation, right? So let's look at context first. Everybody's getting what context looks like? So in context, you've got operations, which is basically every operation within Pliron will be stored in this particular type. Now, again, with Rust, the whole point about Rust is that you can be very clear about what your types are and what your containers are. Containers are nothing but your data structures, right? So let's look at arena cell, because what is arena cell? Arena cell is actually this. It's type alias.
It's a map too.
Okay, it's a slot map. Everybody remember, it's like a hash map, right?
But slot map, you can put a lot of data into it, right?
We'll talk about that. So a slot map has arena index. This is like the key, and this is the value or the data, right? Key value pairs. This is the key and this is the value. But the thing about the slot map is, when you actually look at the in-memory representation, you will not see a key. You will not see a key. Let me help you with that. So, we wanted to look at context, right? Oh crap, I don't have the shortcuts. What is the shortcut for that? Wait.
Command and
Command
click on it.
12.
Full definition, F12.
Hmm.
What the hell?
Control.
Where is F12 over here, dude? There's no F12 over here.
You have to do press command shift, I guess. Not there.
No function keys.
We'll buy the keyboard.
Oh, wait, I have it. I have function key, but
I knew it.
FN you have to press.
FN is there, yeah.
FN? Bullshit.
Something changed. Context.
I'm added now.
Right?
Context.
In the context.
That is fine, but the keyboard stopped working.
Do you connect it to this thing, Bluetooth?
It is supposed to be connected.
N is pressed. Keyboard got locked out.
I think keyboard went out. You can keep your keyboard, I think.
1 second, we have to press this thing.
Which thing?
It's connected.
What the hell happened? I don't know. Okay, I'll just use the key or the mouse. Okay, let's just deal with that. So if you see this, you've got this is your context.
Yeah.
Right? The context it's a container for storing pretty much all of your IR data. Now let's spend some time talking about, because you have no idea what IR data actually means. We'll spend some time talking about it, right? See, the whole point I want to make is compiler engineering. I don't want you guys to I'm not assuming you guys know anything. All right? Although you know quite a bit, I'm going to assume that you guys don't know anything and operate from there, so that if you have any questions that seem like trivial at the time that you're asking, but actually there's a lot of value to asking that question, just ask it. That's what I'm trying to say. Okay. So think about this. Arena cell, if I went ahead and looked at it, what is an arena cell? It's a slot map. Okay. I already told you that a slot map is very much like a hash map, except that the keys only exist at compile time. So they don't exist in memory. That means runtime, you don't have that. You know why? Because if I went ahead and looked at what a slot map is, you'd see that the slot map is only backed by a vector. A vector is basically a dynamically sized array, correct?
Yeah.
So that's it. This is the actual storage within which you store whatever entities. Entities is a word that you use commonly when you're talking about compile time artifact, like not artifact. When you're talking about compilation of your code, you're basically referring to the pieces that make up your code as entities. What do I mean by pieces? I mean a function. The function, the way you describe a function is you say that this is the function. It takes in how many number of parameters. It returns what value. It returns how many values. What are the types of those input parameters? What is the type of the return value? And it also looks at things like what is the calling convention. All these other things that you talk about, that's how you describe a function. Like if you wanted to describe a function to a machine, you don't describe it to me and you like you say that's a function because the syntax looks like that. That's not how we want to look at it, right? So the way you think about it is you basically say that, okay, the function is an entity. It's got these things. Then you'll have something like an instruction. An instruction is what? LLVM has it, Cranelift has it. They're all instructions. We've seen them. For example, if you see this, this is Cranelift IR. This stuff is Cranelift IR. Okay?
More like Rusty fashion, right?
Yeah. Yes, it is. It's very much like that. So this is Cranelift IR. If you look at it, Cranelift IR has components. The function has these elements to it. It has a calling convention, which is because this is Apple's architecture. And then this is the type of the
Pliron is using Cranelift dependency.
No. This is me. I created a temp test function
Okay.
in Cranelift IR.
Yeah.
Okay, Cranelift IR, this is the test function. And then I said, okay, this is the return type. These are the number of parameters that I need. This is the name. And this person symbol indicates that, this is the function name. Function name in compiler engineering terms is not called function name. It's called symbol name.
Symbol.
Okay?
Yeah.
And this keyword is actually a keyword that says this is the function type.
Symbol.
Right? Symbol, this is a symbol. This is not a symbol.
Okay.
Okay, this is like a keyword, okay?
Like return Apple app stipple.
Yeah, this is the calling convention. That means if you're on an Apple machine, Apple Silicon machine, your calling is a little different. It's not as similar to normal ARM64.
Okay.
That's why you want to specify that. This is all part of the function signature, right? This is what a function makes up. Now, if this is one part. Now, if I come here and I look at IAD is an instruction. What is an instruction? What are the components of an instruction, if I ask you?
It has opcode, it has a source and destination.
Operands.
It has operands.
Hmm.
Then it has a return value. Right? These three are the basics that at least we should know about. There's a few more, there's quite a few more, but at least at the basic level you should know this much.
Yeah.
So if you know that much, you can go back. I don't know how to go back. Anyway,
We used to use command minus.
But that is not working now, currently.
And the up arrow you can
wait. What you said is correct.
in the search.
Command minus? No.
Command shift manual, right?
No, that's just going to.
Command only.
I have that mouse with which we can go back. Which I want to use that wireless mouse.
No, but there might be a thing, no?
This button, we can
Go back.
navigate in the code.
How do we add this? This one, huh?
Now go inside the
Oh, it's already
definition.
working. Whoa.
Go inside the definition. Now try to come back.
Hey.
Yeah.
Okay, so that's a sort map, and then we say, so we were basically saying the backing store for a slot map is just a vec. There's nothing more in it. So given that, you might be wondering, okay, how the hell do we use the key then? Is the question, right? This method that you see a similar implementation even in Cranelift also, right? This is a very condensed way of storing stuff. At the end of the day, all your stuff is stored in a vec, but you can pull stuff out of it using a key. But the key is not really, there's no storage for the key.
It's just an index.
Okay, it's an index. So watch what happens. Arena index, you'll jump to here. Okay. What is this arena index? Is actually, it's actually defined within a macro. And by the way, a couple of things that you should definitely know is this crate makes use of procedural macros quite a bit. And there is a very specific reason. It's actually, so far you've heard me say, don't use procedural macros. It's just a headache working with them, correct?
Mm-hmm.
In this case, it's the best choice that the authors actually made. The reason for that is because in something like Cranelift, I had to completely learn a different language. It's called a domain-specific language. That language is specifically designed for Cranelift to create rules in Cranelift. I had to learn that language in order to basically work with Cranelift.
So what you showed, that function is a domain-specific language?
No, that is just Cranelift IR.
Yeah.
Okay, domain-specific language is a little different. Let me see if I can show you that. Just connect.
I have to connect and just Wi-Fi. It's on.
Turn it off and turn it on. So if you go here and if I looked at something like Wasm time and I went into Cranelift and I looked at code gen and let's just say I went into so I want to go where okay, see this? Not this. Hey, what happened? I forgot, man. Where are my rules? Where are the rules, dude? You'll have to write domain.
The second one, dominant tree.
No. At least there must be one file here. Where are all the IL rules?
I'm saying IL, right?
Wait, where did we put all the IL rules, dude? supposed to be in here somewhere. What am I doing? It's right here. Okay, so just click on IL. You see this? This is pretty much a domain-specific language that was invented. This is a domain-specific language that was pretty much invented for Cranelift to write all your rules.
Okay.
And this is definitely not Rust, etc. But I believe the Cranelift team believes that this is the best way to go. I wouldn't be the best person to talk about whether or not they should have just gone with procedural macros. But this is one way of doing things. You can basically invent a new language with a very specific purpose. The purpose of that language is not to write programs for every other general purpose programs, but for a very specific thing.
Yeah.
So this IL code is actually compiled with ILEC, which is somewhere here. Okay, there's many places where IL is, but basically IL is compiled using an IL compiler, and that IL compiler will produce Rust code. Get it? Instead of you writing it by hand, the Rust code, you can write these rules so that it will generate the Rust code. The reason they wrote something like this instead of writing it by hand is because it's massive to write it by hand. You can generate this procedurally. So technically this could have been done with a macro, a procedural macro. But they didn't do it. Okay. On the other hand, somebody like Pliron comes out and says, which is this case, you will see this is not a procedural macro, but there's a lot of procedural macros that are built into what is called derive. This is a crate that contains all the procedural macros of Pliron. If you click on source, for example, op, I'll show you any of what op does, but you'll see that this entire, so procedural macros, as you know, the way you write procedural macros is in their own crate. Every procedural macro will be written or implemented in its own crate. And then you pull that crate in as a dependency and then you use the procedural macro. Okay? Because a procedural macro is nothing but you take a bunch of tokens, whatever Rust tokens you take or whatever tokens, and then you produce a token stream. Right? The job of a procedural macro is to generate Rust code. Okay? So that's the point of so we talked about procedural macros because we were talking about this one. This one is not a procedural macro. So if I was to go ahead and just do F12, you'll see that this is basically in the slot map crate. The slot map crate is not something that the author has written, the Pliron author has written.
Okay, this one.
It's third-party crate. Okay. If you see this, you will see that there's basically new key type and a bunch of different macros written over here. But the job of this is, if you go back to, where's my thing? Yeah. That's why I put notes over here. You don't even have to look at it, but I just wanted to show you the code as well. So an arena cell is nothing but a slot map. A slot map is backed by a vector. And in the slot, the vector contains what? Slots. Each slot is actually the piece of data. It has two fields. One is a union field and the other one is a U32. What is a union? You all know what is an enum, right?
Yeah.
This is a tag. The enum has a tag. That means you know which variant it is, right? Unions don't. Okay? They're not very safe to use, but you can use them. There are reasons why you want to use them. I don't want to get into the details of that, but just note that. Okay? So if you see this, data structures in Pliron will look something like this. It's very well made in the sense that it's well thought out, clearly, as to why you need to do what, why are we doing what. We're not just simply using it because we feel like it. Right? All right, so a slot union is basically these two. I presume you already know what manually drop is. So if something is wrapped in a manually drop, it doesn't get dropped automatically when it goes out of scope. You have to manually drop it.
Okay.
Okay. We'll get to why that is.
Also.
Huh?
Interest, yes.
In safe rust, that too. Manually drop is a type that does not implement the drop rate.
Once it goes out of scope, it won't drop.
If you implement this, it will not go out of scope.
If you wrap any T inside manually drop,
Hmm.
it will not drop.
Then it is a normal point, smart point.
Smart pointer is not this thing. Smart pointer is smart. Okay.
They will implement
It's like in C also there
In
is
C.
called free function. Similarly,
Like that.
So think about it the same way. There's a reason why you need that. Why? Just think about it. Why do you need that? Okay, I really need to remove this, but I'll remove it later. But think about it. Why do you think you need this? Because I can quickly go ahead and look it up.
even if it goes out of scope,
Yeah,
then also it won't drop.
correct.
The data will be still in memory.
Exactly. What's happening here is, if you go and look at this particular piece, where is that? You look at this thing carefully. What did you say? This is a union, correct?
Yeah.
And a union can technically, it's like an enum. That means you can either store, you can store multiple variants inside of it. The thing about an enum is it takes up as much space as the largest variant. Right?
That's what union does, yeah.
Right? The same thing happens over here. If you don't want to lose, like if you drop something, it goes out of scope. You can no longer access it in Rust. If I want the field to be around, but I just want to remove the contents of it. There's no real way. You drop the type, you drop the entire thing. You drop the union itself. In this case, there are actually two pieces that you can put in there. Next free or manually drop T. So a union can be either one of these values.
Yeah.
Make sense? It's like an enum. So effectively, I can take up as much space as T is in here. And then in the same thing, I can store a U32. Get it? I can just overwrite whatever's in there. I don't drop it, but I overwrite whatever's in there. If I want to free it, I'll put a U32 in there. So I'm without freeing stuff, I'm reclaiming that. If I drop it, the union goes away. Like,
Yeah, it's not supposed to go away because it's like tag.
Next
Correct.
three will go.
yeah, the whole point is that you don't want to lose the slot. There's an actual reason that exists, right? Make sense? Questions? Nothing? Yeah, so there are some notes over here. Slot map is essentially a wrapper for a vector slots. Each slot can either store IR data or act as metadata for the free list when it is vacant. That's what the slot is. That's what I told you. Keys are of type arena index, which implement the key trait. That means now we're coming to the key part, which is, you saw that arena index is the key in the slot map. And if you see this over here, arena index, when you expand this macro, produces this. Okay, so an arena index is basically a wrapper for key data. Make sense?
Yeah.
And what is key data? This is what key data is. Key data contains an index and a version. Getting it? So the reason and plus this thing has to implement the key trait. If it implements the key trait, then you're good. Then this big thing becomes a key. Got it?
Yeah.
That's how we do things in Rust, right? The reason I'm like
Where
walking
does mention how to implement key trait?
here, I'll have to show you that I just copied this over here. Keys have to implement this trait to access stored values. You cannot become an arena index without implementing the key trait. Get it? Okay, slot map also includes a helper macro to create new key types, which is why the new key type is there, which is what you saw here. Where is that? Yeah, this one. And then in Pliron, each type of slot map wraps its key in a pointer. We'll get to the PTR. PTR is another important. Yes, it's actually the way the author obviously is from C++. So the naming conventions are a little like, they're very C-like and very LLVM-like. Because he's a compiler engineer, it makes sense, right? So anyway, the thing is, if you actually use types for your key, you can't use the wrong key for the wrong map. For example, if I wanted to index into a web, all indexes are integers, usually unsigned integers, right?
Yeah.
If I want to specifically access an element inside a map, inside one of these arena cells, if I can create a typed version of the key, and only that typed version of the key has access to that map, then I can't accidentally use the wrong key to access any element in a map, right?
Yeah.
Makes sense?
Yeah.
That's part of why you want to use the whole type safety pass.
But all the keys will be having the same type, right?
Not really, no. So if you see this, they're all an arena index, correct?
Yeah.
But the PTR piece that I was talking about, which is this, which I will get to, will take that and wrap it. So if you, let me just show you that first. We directly entered here. Yeah, here. The PTR is what wraps an arena index.
Yeah.
All arena indexes are the same type. The moment I put it in here, and notice how you do this. T implements arena object, but what is arena object? It's phantom data. T does not exist. T only exists at compile time. Now this is a way. Many times I think you guys have got confused with why the hell do we need phantom data,
Phantom data, yeah.
right?
Yeah.
Here's why. You need the phantom data because you need the information at compile time, but you don't really need it at runtime. That means in memory representation there must be no dummy.
Okay.
You only need this dummy so that the compiler can do all the checking and the type safety and stuff. That's why you use the phantom data. Make sense?
Yeah.
So if you see this, you take any arena index and you wrap it in a pointer. If you wrap it in a pointer, it becomes the specific key. For that, so you can have a slot map for operations, like you see in context over here. You have a slot map for operations or arena cell for operations, an arena cell for basic blocks, an arena cell for regions. These are the three most important things. You have it. Everything is inside a arena cell. Correct? The rest of them we'll get to, which is dialect. This is a standard hash map. Except FX hash map is basically a third-party crate where it's a faster hash map. Okay, that's all you need to know. So you got dialects and ops. These ops are not operations. This field is there for different reasons. It's there for registration. We'll talk about that later. I don't think we'll get to that today. Make sense?
Yeah.
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 Okay. Now, so we learned about keys. We learned about arena cells and slot maps. We learned about most of what the context data structure does. It's a storage container. It holds all these elements or all these things. Correct?
Yeah.
Now, I will not get to typecasting right away because it's going to be like a little more weird. We'll get to that when we get to that. Okay? But effectively speaking,
Lazy locks.
you'll have things like lazy locks, and you'll have signatures that look like this. Okay, and then you'll have something called distributed slice, which is a third-party crate, which we'll also look at. Actually, let me see if I can explain this right away, because I wanted to explain that, and then I'll show you a full example, so that in your head at least you should know what you're going to be dealing with. Make sense? Fair?
Yes.
Okay, so you saw the entire context structure, right? Now, let's just switch to VS Code. And we are right now here. I just showed you the entire context, which is this. Now let's go back. Yeah. So what I've done is, I have written a dialect called Pliron Cliff. So let me just minimize this. So this Pliron LLVM is the LLVM dialect in Pliron. So LLVM-IR, if that's converted to Pliron version of it, it's called Pliron LLVM. I use the same naming convention and created Pliron Cliff, which is Cranelift IR. Okay?
Okay.
So, by the way, Cliff is basically Cranelift intermediate format. That's why it's IF.
Okay.
Okay?
So you mainly wrote the Cliff part, right?
Yeah, I only wrote this folder. That's all.
Pliron is already there. Like he
It's
wrote
already
it,
there.
he wrote for
In
right?
fact, Pliron Cliff is basically using Pliron LLVM as the starting point. I just took much of what he wrote, like most of what he wrote, created Pliron Cliff, and then the main conversion part is what I wrote.
Okay.
I'll show you what that looks like anyway. So if you see this, you've got, like I've got two folders in here. This one I will explain. This has nothing to do with Cliff. This is just data that you probably need if you're learning this, right? You really need to know about this. Source, inside source, you will see a couple of things. You'll have, it's a lib.rs, it's a library, all right? You'll have ops, okay? You'll have attributes, and I haven't added it, but I will add it right now. You'll also have types. What the spelling of types? Types dot rs. Okay, you'll have types dot rs. You have attributes. You have operations. You'll have something called operation interfaces.
Yeah.
They're nothing but traits. Fancy word. Okay. And then you'll have one file called from Cliff IR to Pliron Cliff. That's what this file does. First, you define everything inside all these places. That means you define your ops over here, you define your attributes over here, you define your types over here for your IR. In this case, for Cliff IR, we will define the types here. Got it? And then from there, we will go ahead and implement how to convert from Cliff IR. If you give me Cliff IR, how to convert that to Pliron Cliff. Got it? So, let me show you the first piece. Ops. So if you see ops, you guys can see this, right?
Yes.
Actually, no, let me make this small. So if you see this, it's very simple. And I don't even have to do much because all of this was already implemented for me. That's why this is the key part that I was trying to say. To get to this point, with the amount of time that I had, I think a couple of hours is what I needed, that's all. To figure out stuff. Versus MLIR and LLVM and all that stuff. Right? So if you see this, we have the return op. So all you do is, whenever you want to define an op, any op, it's basically a unit struct.
I think
You just write this, and then you annotate it with these procedural macros. You put these two macros on top of it, this thing becomes an op.
okay.
So you don't have to put the second one. At a bare minimum, you have to put the first one.
Okay.
What does it do? I didn't want to waste your time, so I already expanded the output. Okay. What does it do? You simply go to, where are we? Op, no, we're in op. Wait. I don't want op interfaces right now. So I just move that. So I expanded the entire crate. So all procedural macros have been expanded. Now, when I go look at it, the first thing I want to see is what is the return up. I put those two macros on it. What did it give me? It gave me this first. For the first one, for the first procedural macro, it just expanded return up into a PTR operation.
Pointed to a Pliron as operation.
Correct. You already know what that is because you already saw it. Because that is what this is. So effectively, you created an index. When I mark a unit struct with the def op macro, it will expand to basically it'll just create a pointer to the operation, which means it's an index to some operation that is present inside the slot map or the arena cell. Yes? Make sense?
Yeah.
So that's the first thing. What happened? You come in between. Come in between. You come in between. It's fine, man. I'm just kidding. Anyway, so does this make sense?
Yeah.
It's going to be quite important for us.
Mainly, you're going to get a key here, right?
The whole point about this entire thing that we see, all these things about abstractions. Why do we need these abstractions? Because the moment you start writing all this, you'll be like, what is going on? If you just normally wrote it like, it's not like a production level project, you just want to do some prototyping. You can easily go ahead and say, okay, let me put this here.
Everything
You can just remove all that and you'll be able to do your stuff. But when you start working with an actual project and you have, I don't know, let's assume you have any program can run into millions of instructions.
Yeah.
How the hell are you going to manage it? Get what I'm saying? It doesn't make sense when I talk about all this like this. But the moment you start looking at program level stuff, you begin to say that, okay, you'll be wondering, why is the Rust compiler taking so long to compile? Why does this take up so much space in my thing? Another question. These decisions matter. Right? Make sense?
Yeah.
Okay. So, that is what we've done so far. So I wanted to show you that so that you understand what that operation expands to.
Yeah.
And then the second macro expands to this. Plus all this nonsense that you see at the bottom. There's some huge stuff that you'll see. Is nothing much. It's just a closure that's being created and stored somewhere. You are generating a function and you're storing that function as a function pointer in some array. That's the whole thing that's happening. Alright? And I'll tell you why that's happening, but later. Make sense? Yes? Any questions? So far? And then, as usual, you'll also start the def macro will also, let me also show you that. I won't confuse you with the second macro, but the first macro should give you enough input so that you understand what I'm saying. So, let's recap. If you see the first macro says what? It just says def op. Derive op interface implementation is the second macro. So if I was to go ahead and just go to definition, I'm going to where? See where I'm going? Where am I? I'm in
Pliron device.
Pliron derive. In Pliron derive, I went to this thing. So I straight away drop into this and I see that all I'm doing is I'm calling some other def op, which if I go into, I'll jump here. So if you see that I'm just parsing the name and the input that is given to me. The input is nothing but whatever the unit struct I give. Okay. And finally I call this, which is derive. So if I check this, I jump here. If you see this closely, you'll do some checks and balances, you'll do all that. And then at some point, you will see that I'm going to be calling, where is that? I'm going to be calling these two tokens. In this two tokens trait, I'll be calling this two tokens method. The moment I call this, you will see this struct identity generics and then this entire thing. This is exactly what gets created in the cargo expand. If you see closely, let me just minimize this. If you see this, visibility, struct, are there any other identifiers here and there any generics over here? And then this, and you note and you look at this closely, that's exactly what gets created, right? This with the attributes and all of that gets created over here. Makes sense? Along with what? Clone, copy, partial, equal, all those are auto-derived. So what happens is, those things are, when you say auto-derived, they're not like auto-derived, they're actually derived. Get it? They're actually implemented. Yes? Because none of you have actually written a procedural macro fully. You understand what it is, but you've never written one. That's why I'm walking through this.
That which we use that macro.
That's a macro rules macro.
Rules.
Okay. Procedural macros are very powerful, is why they say it.
Declarative.
Declarative macros is the other one. Macro rules macro. Okay? Make sense? So all these things get also implemented.
We derive these traits, right? Yeah. Like we derive them and we don't implement them, right?
We don't implement them. They get auto-implemented.
Auto-implemented.
Why do they get auto-implemented?
Generic.
Yeah, what happens is, you just say derive.
Yeah.
If it's derivable, the compiler is going to derive them from you automatically. If it's not derivable, that's when you get an error.
We have to write it.
You have to write it yourself. Right? Make sense? And the op, I want to go back there to derive. This is done. Then at the end of it, it also goes ahead and says tokens extend and says go ahead and call impl op trait. So do the definition of the struct and then do the impl op trait, which is here. What is the impl op trait? It's impl op. If you actually go down, you will see that this is also an implementation that is created. This is what you see. You can do a get operation, a wrap operation, a get op ID, get static op ID, verify interfaces, all those things are all implemented here. Make sense? This is a procedural macro. Now you should be getting the sense, why am I talking about it? It makes so much sense to implement it like this rather than use a domain-specific language. Because here's what happens. If you went ahead and looked at something like MLIR, all of this will be written in what is called a table gen language, which is a domain-specific language for MLIR. You'll be learning a new language. Here this is Rust. Of course, this is procedural macros, but Rust.
Actually, when the implementation says it, there are like generic implementations, but this macro will connect those.
The macro, if you ever annotate, matlab, if you ever place the macro on top of whatever input that you want to give it, it will produce whatever code gen that you've implemented. That is the job of the macro. Good? Yeah? So far this makes sense? Yeah. I'm not going to go to the second macro because we will come to it. Okay, now let's just close this a bit, just back up, and then we will break in 15 minutes. So where was we? We just talked about the return op. So this op is how I am defining cliff return. This is an IR that I am defining that says this op.
Return you wrote that.
Yes. This op is basically going to be the equivalent to Cranelift IR's return instruction.
Okay.
So I'll show you how that happens. So I am saying that let me create one op. This is the op. So whenever I see return in cliff IR, I'll call this op.
call the
I'll call this op. I'll replace it with this. Pattern matching.
because you have the same types there.
Here it will create
Cliff
an
IR is separate.
optimized
Whenever I'm going to parse the cliff IR. In the cliff IR, when I'm parsing it, whenever I come across return, something like this. For example, this is cliff IR. I'm parsing it. I hit return.
Yeah.
The moment I hit return, I'll replace this in my store, my containers that in my context,
With the
data structure. I will say that I saw this, so you basically add a return op.
Yeah.
I saw this add op, so you add an add op. Right? That's kind of what I did over here. Return op is 1, and then I have add op. Where is that? Here. Add op is implemented differently because it's a like add and sub and all can be implemented in the similar manner. I don't need to write all that. So we created a small macro rules macro. This is a macro rules macro because it's implemented in line. Here you can see there's no separate create amount. So when I do an add op, it will add this macro as well and then implement it. That's all it's doing. And if you go look at the cargo expanded output, you will see that. So you see these macros? Right after this, there's a printable, there's a parsable, all this stuff is fine, but wait. You'll see again add op, same thing. Add op, same thing.
Yeah.
And then you start seeing the entire, all those second macros that were implemented, you'll see the same thing for it. For example, if I scroll down, this is because there's too many traits over there to implement. This part I will explain tomorrow. But if you see this, again, clone, copy, equality, equal, hash, again, get operation, wrap operation, static ID, same things are implemented. Make sense? Yeah? So the exact same thing for return op, for add op is also implemented, but if you go look at it, the implementation looks different. That means the way I wrote it, it looks different because I'm using a macro. Before the procedural macro, I'm using a macro rules macro so that I don't have to write it again and again and again.
So this we can use for any add sub.
Yeah. Any binary operation.
Binary operation.
Any binary operation, I can just use this. I don't have to like completely write it. Right?
And similarly, we have to parse each and we have to write our own op for each operation.
Correct. So how many operations? Oh, very good question. That is the job that we have right now, that is why I've tabulated all the opcodes. Okay. So right now we've only implemented return
and
where the hell is add? Add is on top now. So
This is the number of operations that this thing has. Cranelift.
yeah, it has about 107
Okay.
instructions.
we had 70 for LLVM.
LLVM-IR. Somewhere here there's an add dude. Where's the add? Okay, wait, it's at the bottom. Just look at the number of versions of add, okay? See this? iAdd. This is the one that we're implementing. But there is a uAdd, iAdd immediate. Then there is a uAdd overflow.
This enum is taken from where?
From the Cranelift implementation. Okay. You won't find it in the Cranelift source code. This is generated again. This is another macro in the DAM implementation. So unless you actually go ahead and compile it.
You generated a Cranelift IR. From that IR,
No. This file is generated by a macro in the Cranelift implementation.
Oh, is it?
Right.
Okay.
So I had to pull it from. I had to pull it from the target directory. Just so that's it. Okay. You get all this. So you get all these things, and you can clearly see. The good thing is they've clearly mentioned what to do with what. I don't have to implement all of this because some of this is vector instructions. Unless you need them, you don't deal with them. But you can see this float add, float sub, like everything is, it clearly says what is binary, what is not binary. All that stuff is there. So how many opcodes? You got your answer? Okay.
But what is the difference now in your implementation and in this thing, Cranelift implementation?
No implementation. First things first, you convert. After you convert, you do your analysis and your transformation.
Now you have done for add. Even Cranelift add is there. So what's the difference over there?
There should be no difference.
Only conversion.
Only conversion. The reason you're converting is because I want it in this format. It's like this. It's in one format. I want you to convert it to this format so that I can do some things with that. In the existing format, I can't do shit. That's the problem.
And after that, again, I have to convert back.
Yes.
To LLVM.
To either LLVM or Cranelift.
Oh,
Depends.
The same will take Cranelift here and then Pliron and again.
For example, if you were to go look at the source code here, you see that there's Pliron LLVM. We expand this, you will see that he's already done it. For example, he's created attributes, which is all, these are all the attributes that are present in LLVM-IR. These are all the ops that are present in LLVM-IR. So if you look here, the return op is exactly the same. Okay. And then if you look at the thing, he's also doing from LLVM-IR. That means I'll take LLVM-IR and I'll convert it to Pliron LLVM. For that, he's using all this, which I have not used because this makes no sense for me. Alright? And then types, the types that are present in Pliron LLVM that also are being implemented. For example, there's a struct type in LLVM. LLVM has a type called struct. We can't implement it because Cranelift doesn't have it. We won't implement it. And then there is, this is not a type, but so if you just scroll down a bit, I'm just looking for array type. These are all the types that are present in LLVM-IR. Okay. If you wanted to, I don't know if you, do we have any LLM? No, wait. Great. I don't want to share this on screen, but fine. Anyway,
Using DeepSeek.
I'm using anything that goes. All of them are same shit. They've been stealing everyone's data. Okay.
DeepSeek respond late.
Yeah, it's because people were hammering it. But now it's a little better. By the way, did you guys remember, saw the thing that I shared that thing with the.
On LinkedIn.
No. That new chat app I shared with you. It's called what? LeChat. LeChat. I shared with you, right? LeChat I shared with you. It's a freaking faker, okay? There are two things in it. One is, so LeChat is a French company that's doing the same thing that OpenAI does, trying to build the best models, etc. So they built one model, they rolled it out. It's pretty popular apparently. One thing I noticed is the moment I logged in and I started asking questions, the responses were lightning quick. Lightning quick. It's not like no. The reason is because at the back end, they were partnering with Cerebrus. Cerebrus is this new company that makes a wafer scale engine, basically an AI accelerator. It's a new kind of architecture that they want to do. Nothing new. Basically, they added more memory. They added more memory directly into the GPU. That means the cache that you usually call a cache, they made it gigabytes. Anyway, forget that. So that was being very fast. That thing you'll only get like 3 or 4, questions. After that, that's it. It'll attract you with the speed, and then you get the normal speed. Bullshit, man. People are all. Anyway, make sense? So.
Sorry, what you said, like LLVM it is done. Now we are doing for Cranelift IR.
Yes, LLVM it is ongoing. It's not done. He's implemented many opcodes.
Yeah.
He's going to be working on it quite a bit. Cranelift is what we need to be implementing. Make sense?
So if you build this thing, right, a cliff, we can use it, Cranelift here, we can use both sides, right? For example, after MIR also we can use, and we can use after optimizing it, again we can give it to this thing to LLVM-IR.
You can do whatever you want because it's an IR. You can flip from one to the other. If it's not there, the only thing you have to do is implement it. And by now you should know implementation is not simple. One problem is getting started. That's what I'm trying to solve right now. That means getting started problem I'm solving. It's solved. Think about it that way. The second problem is
What am I building?
completing it. That means if I build Pliron cliff, you don't want it to be a prototype and all. What are you guys doing?
I have to set up this thing.
The call.
Yes.
I'll anyway break.
Yes.
It's in 1 minute.
Yes, RD is called.
Okay. Makes sense
Yeah.
so far? So we talked about the two different dialects. One that's already implemented, and in Pliron cliff we basically said, how many ops does cliff contain and how many ops should we be translating. And we also talked about what an op is, an op definition, how do you define it. The same thing holds true for types and attributes, which I have not implemented yet. And then if you go ahead and look at something like from cliff IR, as we will discuss once we restart, this is what is completely new for my implementation, where I take in cliff IR and produce Pliron cliff. Okay, how do we do that? Something that I'm going to show you after this.
Okay.
Got it? Yeah. Any questions?
I still have a doubt, how do you link MIR also with this thing? How do you link the MIR with this?
Why are you still on MIR? MIR is in Rust.
Yeah, but you need to, this is a middle guy, right?
So here's what I'll say. Let me help you with this. You write a dialect called Pliron MIR.
That implement, right?
You have to implement that?
Yeah.
Once you've implemented that, then you can write transformations from Pliron MIR to Pliron cliff.
Yeah.
After you've done that, maybe you have more transformations in Pliron cliff. You do that also. Then from Pliron cliff, you produce cliff.
Yeah. But cliff is completely Cranelift thing.
Yeah. We are not touching the front end part, we are not touching the back end part. We're sitting in the middle. Got it?
Yeah.
Okay. Alright guys, that's it. I'm going to stop if there are any questions because we got a call after that. We'll reconvene. Okay?
Yeah.